Swayam Prabha. Digital India. Educated India.
Hello everyone. Now let's start with lecture 3 of module 12. In lecture 3 today we are going to discuss about subduction zones. More specifically, we will be discussing about the formation of the plate convergence, or you can say the forms of or the types of the plate convergence, and also we will classify the earthquakes at the subduction zones based on the hypocentral depth, and then we will be discussing about earthquakes in subducting slabs. As far as the recap of previous lectures are concerned, we learnt about plate tectonics treats the Earth's outer shell as made up of about 15 rigid plates about 100 km thick, which moves relative to each other at a speed of few centimeter per year. We observe spreading centers, subduction zones, and transform fault as three types of plate boundaries. So spreading centers are basically divergent plate boundaries, and subduction zones are convergent plate boundaries, and transform faults are basically the boundaries where the plates move horizontally relative to each other. So these are the types of plate boundaries. Volcanism, hydrothermal circulation through cooling oceanic lithosphere, and the cycle of uplift and erosion are processes by which the solid earth interacts with the ocean and the atmosphere. The interplate earthquakes both delineate plate boundaries and show the motion occurring there. Euler theorem states that the displacement of any rigid body, so a plate in this case, with one point, in this case the center of the earth, fixed, is a rotation about an axis. Hotspots and deep mantle plumes are used to track the absolute plate motion. The relative and absolute Euler vectors are simply treated as omega sub ij is equal to omega I minus omega j. The temperature as a function of depth and time is given by one-dimensional heat flow equation, that is at the spreading ridges. So at the spreading ridges, the magma is bulging up and forming a new lithosphere, and with time the age of the lithosphere increases, and with depth also it increases. So the temperature as a function of depth and time is given by one-dimensional heat flow equation, that is del T by del T is equal to K by rho Cp del a square T as a function of z comma T by del Z square is equal to kappa del square T z comma T by del Z square. And the solution for this differential equation may be written something like this, where the temperature at a depth and time T is equal to Ts. Ts is the surface temperature or the ocean floor temperature, in bracket Tm, that is the temperature at the asthenosphere or the half space, minus Ts, error function which has the argument z by 2 under root kappa T, and error function is written by 2 by under root pi integral 0 to s e to the power minus sigma square d sigma. The temperature at depth z for material of age t, t as a function of z comma t is equal to tm, error function z by 2 under root kappa t. An isotherm is a curve on which the argument of error function is constant. So for the isotherm we can keep this as constant, and z will be replaced by z sub c or z in subscript c. So z in subscript c will be equal to 2 under root kappa t. So you can see the depth of the isotherm will be proportional to under root of the age of the lithosphere. The temperature and thus density in the cooling lithosphere vary such that at the time z comma t or at the point z comma t, the temperature is T z comma t and the corresponding density is rho z comma t is equal to rho m plus del rho by del t Tz comma T minus Tm is equal to rho m plus rho dash z comma T. Density perturbation for the half space cooling model is rho prime z comma T is equal to alpha rho m Tm minus Tz comma T, and in terms of the coefficient of thermal expansion alpha is equal to alpha rho m Tm in bracket 1 minus error function z by under root 2 under root kappa T. The isostatic condition, that means the ocean floor depth, can be found out using this formula 1 by rho m minus rho w. Rho w is the density of the water, integral ht to mt rho dash z comma t dz. So basically there is this rift zone here, and then you will consider a vertical section here, and let's suppose there is one another vertical section at t is equal to t, and then using the principle of isostasy, this formula can be derived, and where we are keeping the mass in this column, vertical column, at the location of the ridge, and at time t at this particular vertical section equal, then you can get this isostatic condition for the ocean depth. And here the ht is the water depth column, and this mt is the thickness of the asthenosphere, or the lithosphere, I'm sorry, it should be lithosphere. The ocean depth should increase as square root of the plate age. So it will be equal to ht is equal to 2 under root kappa t by pi alpha rho m tm by rho m minus rho w. For plate model, the temperature vary as a function, and depth is given as tx comma z is equal to tm in bracket z by l summation over n is equal to 1 to infinity cn exponential minus beta n x by l sin n pi z by l. Now let's start with the lecture today. We are going to discuss about the subduction zones. As you know, we have discussed about spreading center in the previous lecture, where the magma is bulging up and forming the new lithosphere, and that is basically considered to be the upwelling limbs of the mantle convection system, and that reflects the processes forming the oceanic lithosphere there. So this is what it is written here: the shallow deep earthquake, or the shallow depth earthquakes at spreading centers are upwelling limbs of the mantle convection system that reflects the processes forming oceanic lithosphere there. And similarly, there are the subduction zones where the mantle or the lithosphere is sinking down and being basically compensated into the mantle. So in similar way, earthquakes at the subduction zones, that is basically downwelling limbs of the convection system, reflects the processes by which oceanic lithosphere re-enters into the mantle. So now look at this diagram that basically depicts the processes associated with the subduction of one oceanic plate beneath another. So you can see this is the oceanic plate here, and this is another oceanic plate here, and you can see this is subducting beneath this particular plate here, and when it's subducting, then it is forming this slab like structure here, and top of which on the other plate you can see the volcanic arcs are forming, and behind which there is the back arc basin forming here in the form of the mid-Atlantic ridges, or you can say the mid-oceanic ridges, and this particular back arc basin is basically opening a new ocean basin over here, and this is what the construction looks like. So you can see here you have the high viscosity mesosphere, here is the low viscosity asthenosphere, and this basically bulging up and forming the new lithosphere around the mid-oceanic ridges, and this basically being compensated at the subduction zone over here. And now let's talk about different kind of subduction zone. First we will be talking about flip-flop polarity reversal subduction. There is a thought by various geologists that the subduction where one plate is going down over the another plate underneath the another plate, or you can say there is one overriding plate and another plate is underriding plate. So this particular phenomena gets reversed. That means the plate that was overriding becomes underriding, and the underriding plate become overriding over a period of time. So this is what it is known as the flip-flop or the polarity reversal subduction, and this basically explained as subduction polarity reversal is a geologic process in which two converging plates switch roles. The overlying plate becomes the downgoing plate and vice versa, and this particular phenomena is also known as subduction switch or the flipping of the subduction polarity or the subduction polarity reversal. So you can see here there is this plate which is basically subducting down underneath the overlying plate, and in the another picture here the subducting plate that was in the previous in this particular figure is becoming the overlying plate, and this particular is basically subducting down. And if you want to look at the example, there is one example from Caledonides in Ireland and Alps Apennines in Italy. There is another subduction type, that is flat slab subduction. You can see there is a flat portion of the subducting slab here, and then finally it gradually goes down into the mantle. So this is basically characterized by low subduction angle or less than 30 degree to horizontal beyond the seismogenic layer, and a resumption of normal subduction far from the trench. A broader definition of flat slab subduction includes any shallowly dipping lower plate as in western Mexico, and it has taken from Wikipedia. Another type of subduction is oblique subduction. This is the most predominant subduction that you will find all over the globe, and oblique subduction is a form of subduction, or you can say that means a process or the tectonic process involving the convergence of two plates where the denser plate descends into the Earth's interior, for which the convergence direction differs from 90 degree to plate boundary. In general, the obliquity angle is between 15 degree to 30 degree. The subduction zone with high obliquity angle includes Sunda Trench, where it is around 60 degree, and the Raikuku arc, that is having the very high oblique angle or the subduction angle. There is another kind of subduction, that is rollback subduction, in which the negatively buoyant slab, if you will consider like as compared to the asthenosphere, is long and it is very heavy and anchored in the mantle, and it can sink more rapidly than the rate of plate convergence. The gravitationally unstable slab becomes steeper, which produces a migration of the hinge zone and the bulge where the slab bends away from the arc. So basically what happens, so this slab, when it goes down due to its heaviness, it basically molded back away from the zone of subduction. So this basically this kind of migration at the hinge zone happens and the bulge where the slab bends away from the arc. Now let's talk about the forms of the plate convergence, that means types of the plate convergence. One is the oceanic lithosphere, another is oceanic continental lithosphere, and then we have the continental convergence. These three types we are going to discuss about. Let's first discuss about the oceanic lithosphere. In this particular kind of subduction or the convergence, the volcanic island arcs forms, and behind which the sea floor spreading occurs, and that basically forms a back arc basin or the marginal sea. So you can see this subducting slab, this is one oceanic plate here, and another oceanic plate is here, and this oceanic plate is sinking down beneath the oceanic plate. This is what is here, and you can see this the oceanic plate when it is sinking down because it is having the lower temperature than the surrounding magma, then the part of which basically forms the volcanic arc just above it on the surface, and beneath which or the behind which there will be a seafloor spreading might be happening, and that will form a back arc basin in this particular area. And then the Mariana Trench, that is one of the example of such kind of oceanic lithosphere convergence plate boundary. The Mariana Trench, deepest ocean trench, is more than 35,000 feet below sea level, and it is the result of Pacific plate moving beneath the Mariana Trench or the Mariana Plate. Now let's talk about oceanic continental lithosphere. When oceanic lithosphere subducts beneath a continent, a mountain chain like the Andes forms on the continent, and oceanic lithosphere forms the Vadati Vanioff zone. So here is the Vadati Vanioff zone, and you can see the oceanic lithosphere here is subducting beneath the continental lithosphere, and that is forming the mountain chain like structures just above over here. The next one is continental lithosphere, that is basically happening in Himalayas as well. And here the continent crust do not subduct, and convergence happens between the two continental plates. And this is similar to the example of Himalayas where the crustal thickening is also happening, mountain building are happening, and the shallow focus earthquakes are also happening, and it does not create any Badati of zone here. Now let's classify the earthquakes that are occurring at the subduction zones. And subduction zone earthquake can differ in depth, tectonic environment, and the focal mechanism. And based on their occurrence depth, it can be classified as shallow focus earthquake, that is having the depth of the hypocenter less than 70 km, intermediate focus earthquake in between 70 to 300 km, and the deep focus earthquake, that is having the depth more than 300 kilometers. Now look at this diagram. This basically is for the various earthquake types that observed at the subduction zones. So you can see just at the place where the two plates are basically migrating, or you can say the converging, the small focus earthquakes are happening, and due to the bending here or the release of the stress here, the great thrust earthquakes may often occur, and it is not always, but the examples are 1960 Chile earthquakes and the 1964 Alaska earthquake. And here you can see the intermediate focus earthquake between 70 to 300 km may occur, and this is at near to the slab top, and it is primarily having a down dip tension. And at the deep seismic zone, that means the deep focus earthquake more than 300 km, it is might be having the single or the double couple mechanism, and this will be having the primarily down dip compression, and dip may vary considerably and depth may vary also considerably. So this is what it is written here. The shallow earthquakes are associated with the interaction between the two plates. The largest and most common of these shallow earthquakes occur at interface between the plates and release the plate motion that has been logged at the plate interface. In addition, shallow earthquakes can occur within both the overriding and the subducting plates. The intermediate and the deep earthquakes form the Badati Benioff zone occur in the cold interiors of the downgoing slab. Now let's talk about the thermal evolution of subduction. The thermal models for subduction is used to gain insight into earthquake and seismic velocity observations. Moreover, seismological observations, thermal models, and calculation of behavior of materials at high temperature and pressure are combined to investigate the complicated regions. The essence of subduction is the penetration and slow heating of a cold slab of lithosphere as it descends into the warmer mantle. Slabs subduct rapidly compared to the time needed for heat conducted from the surrounding mantle to warm them up. Thus, they remain colder, denser, and mechanically stronger than the surrounding mantle. Consequently, transmit seismic waves faster and with less attenuation than the surrounding mantle, making it possible to map slabs and to show that deep earthquakes occur within them. Now look at this diagram which shows the distribution of seismicity with depth in subduction zones. So the question is why we distinguish intermediate and the deep earthquake. If you just look at this number here, the number on the y-axis is representing the log number of the earthquakes, and on the x-axis you have depth in kilometers. So what you will observe, the earthquakes that are happening at the subduction zones, mostly that the earthquakes are happening having the lower peak at the 300 kilometer, and then again it rises at around 600 kilometer depth, and then again it has the minimum value number of earthquakes at 700 kilometers. So this is what it is written here. Seismicity decreases to a minimum near about 300 kilometers. That is why we want to distinguish them in between the intermediate and the deep focus earthquake, because there is a contrast in the number of events that are happening. So number of events are basically minimum at around 300 kilometer depth, and then again it increases, and then it becomes one more time minimum at around 700 kilometer depth. So this is what it says. Deep earthquakes, those below about 300 kilometer, are thus generally treated as distinct from intermediate earthquakes. Deep earthquakes peak at around 600 kilometer and then decline to minimum before 600 kilometers. The possible reason for this distribution of the earthquakes may be the near the surface, the slab is extended by its own weight, whereas at depth it encounters stronger lower mantle material causing down dip compression. The another reason may be the mineral phase transition, or so you can say the mineral phase is changing, that occur at different depth in cold slab than in the surrounding mantle. Now let's talk about the slab pull. The thermal model gives the force driving the subduction due to the integrated negative buoyancy of a slab resulting from density contrast between it and the warmer and the less dense material at the same depth as outside. The force known as the slab pull is the plate driving force due to subduction, and specifically it is the negative buoyancy associated with the cold downgoing limbs of the convection pattern. Its significance for stresses in the downgoing plate and for driving plate motion depends on its size relative to the resisting force at the subduction zone. Slab pull force is balanced by local resistive forces, a combination of the effect of the viscous mantle and the interface between plates. So this is the summary of today's lecture. Earthquakes at subduction zones, downwelling limbs of the convection system reflect the processes by which oceanic lithosphere re-enters the mantle. There are basically three types of convergence. One is oceanic-oceanic, another is oceanic-continental, and the third one is continental-continental plates like in Himalayas. Earthquakes at subduction zones are classified into shallow, intermediate, and the deep focus earthquake. For shallow, less than 70 km, intermediate in between 70 to 300 km, and deep focus is greater than 300 km. On the basis of tectonic environment at subduction zones, we classify the earthquakes into one which occurs due to interaction between plates, that means shallow focus, and other which occurs in cold interior of the downgoing plates. In subduction zones, focal mechanism for shallow earthquake shows down dip tension and down dip compression. Down dip compression is observed deeper than 300 km. Slab pull is the plate driving force due to subduction. Specifically, it is negative buoyancy associated with a cold downgoing limb of the convection pattern. So these are the references for this lecture. Thank you very much. Bye-bye.